In section 7b, we will study rules associated with combining probabilities using the words and or. In this video, we will go over the definitions of independent events and disjoint events. Let's start with the definition of independent events. Suppose we have events E and F. They're two separate events. How do we know that these events are independent? So the word independent is defined here. Two events are independent if the occurrence of the first event, let's say E, does not affect the probability of the second event occurring. So that is the definition of two independent events. If the happening of one does not affect the probability of happening of the other. The simplest example that we can think of is in the experiment of rolling a die. And suppose we roll a die and we define events E and F as E getting a 6, F getting a 3. So events are just written as collection of objects here using the braces. So E is the event of getting a 6 and F is the event of getting a 3. So when a die is rolled, the probability that E happens is 1 out of 6. So the probability of getting a 6 is 1 out of 6. The probability of getting a 3, which is the second event, is also 1 out of 6. So the probability of getting either E or F is 1 out of 6. Now, how do we know that the two events are independent? Suppose we roll a die and we get a 6. The probability of that happening is 1 out of 6. Now, once that is done, so now we know that the first roll we got a 6. And if I ask you the question, what is the probability of getting a 3 in the second roll? Your answer would still be a 1 out of 6 because it really doesn't matter whether we got a 6 in the first roll or a 5 or a 4. It really doesn't matter what happened before we rolled the die again. So if we don't really have to consider what happened before in order to make a decision about the probability of what's going to happen now, then the two events are independent. Now let's look at a second example. Now here we're looking at another standard example of selecting a card from a standard deck. So if a card is selected from a standard deck, the question says, what is the probability of getting a jack in the first draw? So a standard deck contains 52 cards, out of which 4 are jacks. So what is the probability of getting a jack in the first draw? It is 4 out of 52, which is equal to 1 out of 13. Now, the important thing to note here is that the card is now replaced. After we drew the first card, we got a jack, we put it back into the deck. Now the next thing we're going to do is draw another card. And the question is, what is the probability of getting a jack again? Now, if we put the card that we drew previously in the first trial back into the deck, the probability of getting a jack again does not change. So that tells us that the first event of getting a jack in the first draw and the second event of getting a jack in the second draw are completely independent. So knowing that we got a jack in the first draw does not have any effect on the probability of drawing a jack in the second draw. So the two events are independent. That is because the first card was replaced before we drew the second card. Now, suppose we change the condition now. We draw the first card, but we do not replace the card back into the deck. So the probability of getting a jack in the first draw still remains 4 out of 52, which is equal to 1 out of 13, because the deck is intact. So the probability of getting a jack is 4 out of 52. But now we're not going to replace the jack. So what happens in the second draw is we have one jack less and one card less. So what is the probability of drawing a jack the second time? Now, since we did not replace the cards, we only have 3 jacks and 51 cards. So the probability of drawing a jack in the second draw changes to 3 over 51. Now, if we know that the card is not being replaced, what we got in the first draw is an important thing to know before we calculate the probability of getting any card in the second draw. So the knowledge of what happened before is important in determining the probability of what happens in the second draw. So in this case, the events of getting a jack in the second draw and a jack in the first draw are dependent. They cannot be considered as independent. So in example 2, when the card is not replaced in the deck after the first draw, then what happens in the second draw depends on what happened in the first draw. So the events E and F, that is getting a jack in the first draw and getting a jack in the second draw, are what we say dependent. So two events are dependent if the probability of the occurrence of an event depends on the occurrence of the event before it. So if we have to think about what happened before in order to calculate the probability of what's happening now, then the two events that we're talking about are dependent. Now, if two events A and B are dependent, suppose B happens first, so this happens first, and we're trying to figure out the probability of A happening. So A happens next. So if you're trying to figure out the probability of A when we know that B has happened before, we need a symbol for it. So we'd have to call it a conditional probability. So probability of A happening cannot be calculated without knowing what happened before. So that is given that B happened before it. So for dependent events, to figure out the probability of A, we would need to know what happened before A happened. So this is called conditional probability. So the vertical line between the events A and B, we read it as given that. So this notation stands for probability of, as usual, probability of the event A given that B happened. So let's see how we can denote given probability statements using conditional probability. So let's look at the first one. Probability of getting a jack in the second draw, knowing that in the first draw we got a jack. So this is how we write it. Probability of jack in the second draw given that, this vertical line means given that or knowing that, we got a jack in the first draw. So this is how we write down probability of the second event happening, given that a first event happened. Now look at the second one. Probability of getting a 3 in the second roll of a die, knowing that the first roll was a 6, is denoted by this. Probability of, that's how we read P of, this is of, 3 in the second roll, given that we rolled a 6 the first time. So the given that, the vertical lines reads as given that. Now, in the first case, if the card is not replaced, then the two events, getting a jack in the second, depends on whether we got a jack or something else in the first draw. So this is when, for example, when cards are not replaced, we'd absolutely have to know what happened before in order to calculate the probability of what's happening in the second draw. But in this case, we're rolling a die. We get 6 in the first roll, and we're trying to calculate the probability of getting a 3 in the second roll. Do we really need to know what happened in the first roll to figure out the probability of what happened in the second roll? And the answer, we know clearly we don't need to know what happened before, because every time you roll a die, the probability of getting a 6 or a 3 remains the same no matter what happened before. Now, why do we need to know anything about dependent and independent events? The reason why we need to study that is because of this first rule, which is called the general rule of multiplication. And here it's also called the AND rule, because we combine the probabilities of getting the event A and the event B. So the word here is AND. The word is important. So what is the probability of A and B happening? Suppose we know what each probability or probability of each event is. So two events happen, A and then B. So probability of A and B is probability of A times probability of B, given that A happened. So it's basically the probability of A times the probability of B. But in order to calculate the probability of B, we absolutely need to know what happened before. So that is the reason why we have a conditional here. This is a general rule. However, suppose the events A and B are completely independent of each other. So the rule that we're going to use is this. Probability of A and B is equal to probability of A, which is pretty straightforward. It's the probability of the first event. The word AND translates to times probability of B. Now this is where we have to think. If A and B are completely independent of each other, then when we're trying to calculate the probability of the second event B, we do not need to know if A happened before it or not. So it is a simple probability of P of A times P of B. So this is the rule that works for independent events. In the previous slide, we defined independent events and dependent events. We used the idea of independent events and dependent events when we defined the AND rule. Now we're going to define the OR rule in a minute, but In order to apply the OR rule, that is combining events A and B using the word OR and figuring out the probability, we'd first have to know if the events A and B are non-overlapping or disjoint events. Let's look at a simple example to understand the definition of disjoint events. Two events are disjoint if they cannot happen together. They are non-overlapping or disjoint. Now, suppose we toss a coin and consider two events getting heads, getting tails. So the event E is getting heads, the event F is getting tails. Are the events E and F non-overlapping? So the question we need to ask ourselves is, can the two events, getting heads and getting tails, happen at the same time? Can you get heads and tails when you toss a coin once? The answer is no. When we toss a coin, it's either heads or tails, but the two cannot happen together. So therefore, getting heads and getting tails are non-overlapping. Let's look at a second simple example of randomly selecting a person from a group. The first event is that the person selected is a male, and the second event is the person selected is female. Are the events E and F non-overlapping, and why? So the question again we ask ourselves is, can the two events, being male and being female, happen together? Can a person simultaneously be male and female? We know that it is impossible. So being male and being female, the two events, are disjoint events or non-overlapping events. So we've seen examples of non-overlapping events. Now let's look at the definition for overlapping events or not disjoint events. So if two events can happen together simultaneously, then we know that the two events are overlapping events or not disjoint events. So let's look at example 1. Under this definition, we randomly select a person from a group. The two events are being male and being a nurse. Are the two events overlapping, and why? So the question again we ask ourselves is, can the two events E and F happen together? Can a person be male and a nurse? So it is true that the two can happen. If a person is male and a person is also a nurse, then the person is a male nurse. So if this is the set of all males and this is the set of all nurses, they do have an overlap. And who sits in this overlap? A male nurse. So he's a male and a nurse. So he becomes a male nurse. That is a possibility. So the two events are overlapping.